Hi everyone, this is going to be a review of insertion sort. So let's get started by just reviewing how the algorithm works. Okay, so what we're really doing in insertion sort is we move through the elements from left to right. Okay, for each element, we keep swapping it to the left until it's bigger than the left element. Then we say, chill, you're good here. Okay, and in essence, what we do in an insertion sort is we kind of build a sorted sublist from the left-hand side. And eventually, this sorted subarray will encompass the entire array. Okay? So let's just walk through a quick example on the following array. Okay? So we're going to start off by looking at the number 7. And since 7 is the leftmost element, we will leave 7 as is. Then we will look at the number 1, and we will say, are you smaller than 7? And 1 is smaller than 7, so we will swap 1 and 7, and accordingly, this will be the state of the sorted subarray that we're building. Okay? Then we will look at 9, and we will ask ourselves, is 9 bigger or smaller than 7? And we will see 9 is bigger than 7, so 9 will stay as is, and we see that this is the state of our sorted subarray. Okay? Then what we're going to do is we're going to look at the number 4, and we're going to ask ourselves, is 4 bigger or smaller than 9? And we see that 4 is indeed smaller than 9, so 9 and 4 are going to swap. So right now, we have a 4 here and a 9 here. Okay? The next step is we're going to compare 7 and 4, and we're going to say, is 4 smaller or bigger than 7? And we'll see that 4 is smaller than 7, so 4 and 7 will swap, and now it'll look like so. Okay? Finally, we'll compare 1 and 4 together, and we will see that 4 is bigger than 1, so 4 will stay where it is. And then after completing that pass, this will be the resulting state of that subarray that we're building. Okay? And if we keep repeating this process, eventually this entire list will be sorted, right? Because we're growing this green region. Okay. So looking at the runtime, I'm going to claim that the best case runtime is theta of n, and the worst case runtime is theta of n squared. And the first question we want to ask ourselves after why is the runtime like this is, why is the best case different than the worst case, right? Well, intuitively, if we're at a given element, right, let's say that we're at the number 4, it can either perform 0 swaps or it can move all the way to the front, right? There's two extremes here. And depending on the ordering of the initial array, we may have to do a lot of swaps, or we may not have to do many swaps at all. Okay? So when we think about the best and worst case here, the best case situation is where we don't have to perform any swaps, right? We don't have to perform any swaps when the input list is in sorted order. Okay? Sorted ascendingly. Right? So how that can look is like 1, 2, 3, and so on. Okay? Sorry about that. And why does this produce the best case behavior, right? Well, let's think about it. Suppose that I have 1, 2, 3, 4, and so on. Every time that we're at a given element in insertion sort, let's say we're at 4. Notice that 4 is bigger than the element to the left of it. So we're going to keep 4 where it is, and so on. So we're never going to have to do any swapping, and all of the work that we're doing is just looking at each element once. And accordingly, we get a theta of n runtime, right? So let's think about what would produce the worst case behavior, right? When we think about the worst case behavior, we're thinking about the situation where every time we see an element, we have to move that element all the way to the front, right? For the sake of an example, suppose that this element was the number 0, okay? If the number 0 is here, we'd have to move all the way to the front. Well, if it's the case that every time we see an element, we have to move that element all the way to the front, what we can say is that the list is sorted in descending order. Okay? An example of this can be like 5, 4, 3, and so on. Okay? And why does this produce the worst case behavior? Well, looking at the example that I put above, if we're at the number 3, we're going to have to move 3 to the left of everybody that comes before it. Same with 2, same with 1, right? And this gives us n squared behavior because when we're at the number 3, we have to perform swaps equivalent to like its index. So what do I mean by that? Well, looking at, let's use another color, looking at number 5, 5 has to perform 0 swaps. 4 has to perform 1 swap. 3 has to perform 2 swaps. 2 has to perform 3 swaps. And 1 has to perform 4 swaps. So the total amount of swapping that we have to do is this sum, which comes about to n squared asymptotically, right? Which is something we've seen before in this class. So if the amount of swapping that we do is n squared, and we look at n elements, then the total runtime is n squared, because the n squared term dominates, right? Okay, so let's quickly talk about the next point, which is why would we ever use insertion sort? What advantages does it have to offer? So insertion sort is very fast on small inputs, okay? You can just kind of take that for granted. The second one makes a bit more sense, where if the input list is in nearly sorted order, what I mean by that is it looks something like the following, but maybe not as good as this, right? We can see that there's not much swapping that we have to do. In that case, it's pretty advantageous to use insertion sort, right? Okay, so let's finish this off with a quick understanding question. So the runtime of insertion sort can be written as theta of n plus k, where k is the number of inversions. And the question is, why is this the case? Well, let's first recall what an inversion really is. So recall that an inversion happens when we have a pair of elements, let's call that pair x comma y, where x precedes y. What this means is x is earlier than y, but is greater than y, okay? So for example, if we're looking at this array right here, notice that 7 comes before 3 in the array, but 7 is greater than 3, so this is an inversion, okay? On the other hand, if we looked at the pair 1, 7, this is not an inversion because 1 is ordered correctly relative to 7, right? So I like to think about inversions as an out of place pair. What I mean by that is, let's look at the numbers 7 and 2, okay? Notice that if we look at these two numbers, 2 comes after 7 in the array, but it's smaller than 7. So we can kind of think about these pairs as out of place, right? Relative to each other, they're kind of sorted incorrectly, okay? So at this point, pause the video now that you've understood what an inversion is, and try to figure out why is the runtime of insertion sort theta of n plus k, okay? So coming back, hopefully you had a chance to give that a go, and let's walk through why the runtime is theta of n plus k. So what I'm going to claim is that theta of n plus k, the n comes from looking at each element, and the k is the total swaps that we do. Okay, so my claim is that every time we have to swap, it's because we're trying to fix an inversion. Okay, let me write that down. So my claim is that every swap is fixing an inversion. Okay, so let's kind of like justify this claim by looking at our example that we had before. Okay, so before we dive into this example, what I'm going to do is I'm going to define when we have an inversion. Let's say we have some inversion x comma y. If we ever have the inversion x comma y, let's call y the rightmost element in the inversion. Okay. So I'm going to be kind of saying this idea of the rightmost element pretty often in the next few minutes. So when we have an inversion x comma y is going to be the rightmost element in that inversion. Okay. So for a quick example of this, if we look at the inversion between 7 comma 1, 1 is the rightmost element here. Okay. So why is this irrelevant, right? It seems kind of silly that I brought this up. So my claim is that the number of swaps a number does is equal to the number of times it is, let's see if I can fit this in, the rightmost element. Sorry about that, I kind of squeezed it in. So my claim, just to reiterate, is that the number of swaps we have to do for a given number is equal to the number of times it is the rightmost element in an inversion. So let's kind of see what I mean. Well, let's start off with the number 1. Okay, how many inversions exist where 1 is the rightmost element? Well, the only inversion where 1 is the rightmost element is the inversion 7 comma 1, right? 1 is the leftmost element in 0 inversions, and it's the rightmost element in 1 inversion, right? And what I'm going to claim here is that the number of swaps a number does is equal to the number of times it is the rightmost element. So since 1 is the rightmost element in an inversion one time, 1 has to do one swap, right? Because it has to swap before the element that it was part of an inversion with, right? Since 1 and 7 are part of an inversion, we know that 1 must swap to become before 7, okay? Okay, so let's move on to talk about number 9, okay? So how many numbers is 9 the rightmost element in an inversion with? So 9 is never the rightmost element in an inversion, right? Because the only elements that come before 9 are 7 and 1, and 9 is ordered correctly relative to 1 and 7. Okay? So as such, 9 doesn't have to do any swapping, because it's never the rightmost element in any inversions. On the other hand, if we move on to, I'm going to use a different color, if we move on to the number 4, notice here that 4 is the rightmost element in 2 inversions. The inversion 9-4 and the inversion 7-4, right? So what's going to happen here is that we're going to have to swap 4 to come before 9 and 7, okay? So accordingly, 4 has to do 2 swaps, right? Because it must come before 7 and 9. So what we'll see here is that the total number of swaps we do is equal to the total number of inversions, right? Because of this logic right here. So bringing that back, we've successfully shown that the number of inversions is equal to the total number of swaps that we do, right? So the runtime can be represented as theta of n plus k. So hopefully this example solidified your understanding of insertion sort. And yeah, stay tuned for the next video.